Hi. In this video, we are going to start studying the Laplace transform, a new transform. In fact, it's an extension of the Fourier transform. Now, first of all, we have to try to answer the following question. Why do we need such a new transform? What is the basic motivation behind the Laplace transform? Okay. Now, first of all, let us remember that if a signal is absolutely integrable, its Fourier transform exists. Okay, so we first start with this important fact. Remember that if x of t is absolutely integrable, its Fourier transform exists because now absolute integrability means that from minus infinity to plus infinity, magnitude of x of t integrated with respect to t must be finite. Okay, this is the definition of absolute integrability of a signal over the interval, time interval from minus infinity to plus infinity. So we know that x of omega is from minus infinity to plus infinity, x of t e to minus j omega t integrated with respect to t. Okay, well, we look at the magnitude of x of omega. Remember that x of omega is in general complex valued. So its magnitude is the magnitude of this integral, x of t e to minus j omega t integrated with respect to t. Okay, we know that the magnitude of an integral is less than or equal to the integral of the magnitude of the integrand. Magnitude of x of t, magnitude of e to minus j omega t integrated with respect to t. So this is 1, magnitude of e to minus j omega t. In fact, it's the modulus of that complex quantity. Okay, so from here we conclude that magnitude of x of omega is finite for all omega between minus infinity and plus infinity. Okay, let us write it in that form. Provided that x of t is absolutely integrable. Because we started with the Fourier integral, then we looked at the magnitude of the Fourier integral and obtained an upper bound for that magnitude. And that upper bound is just the integral of magnitude of x of t. X of t can be real value, so in that case its magnitude is absolute value. If it's complex value, the magnitude is modulus. So if x of t is absolutely integrable, the Fourier transform of x of t exists and is finite for all omega. Now, for instance, if we have x of t equal to e to minus t u of t, we have x of omega. Now, in fact, let us look at the condition of absolute integrability from minus infinity to plus infinity. Magnitude of x of t integrated with respect to t is just the integral from 0 to infinity. Magnitude of the exponential is just the exponential itself, e to minus t. Since we have u of t, the integral starts from 0. So this is equal to minus e to minus t, evaluated at 0 and infinity. At infinity, as t tends to infinity, e to minus t tends to 0. So the value of this integral is 1. So x of t is absolutely integrable. And remember, x of omega can be calculated as 1 over j omega plus 1. We have calculated this many times before. Now, suppose that our x of t, now consider the signal x of t given by the expression e to t u of t. Okay? Now, obviously, this is a growing exponential, and therefore it is not absolutely integrable. From minus infinity to plus infinity, magnitude of x of t integrated with respect to t is from 0 to infinity, e to t integrated with respect to t. So this is e to t evaluated at 0 and infinity. But we know that this is not bounded, okay, is not finite, since limit as t tends to infinity, e to t is not bounded. It tends to infinity. Okay? Therefore, x of t, the signal x of t, which is equal to e to t u of t, is not absolutely integrable. And therefore, its Fourier transform does not exist. So Fourier transform of x of t, which is e to t u of t, does not exist. Okay, so the question is the following. Do we have to stop at this point, or can we do something to solve this problem? Obviously, the Fourier integral will not be a convergent integral, since the signal is not absolutely integrable, and it's not possible to evaluate the Fourier transform by means of the Fourier integral. So what can we do now? Okay, so the next step will be to introduce a new transform such that we will be able to calculate the transform even for signals which are not absolutely integrable. Okay, so let us see how we can achieve this. Okay, Fourier transform of e to t u of t does not exist. So let us do the following. Instead of evaluating the Fourier transform of e to t u of t, multiply e to t u of t by the function e to minus sigma t, where sigma is a variable. So, let us try to evaluate Fourier transform of e to minus sigma t e to t u of t, where sigma is a real variable okay, let me write this in quotations. Let us try to evaluate the Fourier transform of not e to t u of t, because we are not able to do that, but we multiply e to t u of t by e to minus sigma t, but sigma is not a constant, it's a variable. That is the important point. By choosing the proper range of values of the real variable sigma, such that the integral exists. Now, how can we do this? Now, the Fourier transform of e to minus sigma t e to t u of t is from minus infinity to plus infinity e to minus sigma t e to t u of t e to minus j omega t integrated with respect to t. Now, because of the unit step function, in fact, the integral starts from 0 to infinity. Now, we can combine e to minus sigma t and e to t as e to 1 minus sigma t. Okay? And we have e to minus j omega t integrated with respect to t. Okay? Now, the question is the following. How do we choose the range of values of sigma, such that this integral is convergent? Now, we know that if this exponential term is a decaying exponential, okay, So as t tends to infinity, this exponential term must decay to 0 such that the Fourier transform integral, the Fourier integral exists. In fact, it's the condition of absolute integrability. So this integral exists if from 0 to infinity e to 1 minus sigma t integrated with respect to t is finite. And the condition for the existence of this integral is that sigma must be greater than 1. Therefore, we have a decaying exponential and the integral is finite. So this term is absolutely integrable and therefore the Fourier transform exists. Okay? Now it is clear that if sigma is greater than 1, then this exponent, the term in the exponent will become negative, and therefore we have a decaying exponential and the integral will have a finite value. Fourier transform, therefore, of e to minus sigma t e to t u of t exists. Okay? So it seems that we have a clever way of handling such signals. Signals which are not absolutely integrable, and therefore it's not possible to calculate their Fourier transforms. But if we multiply such a signal, and in our case the signal is the growing exponential e to t u of t, by the exponential term e to minus sigma t, and by choosing the variable sigma, the range of values of the variable sigma suitably, we are able to obtain a convergent integral. Okay? Now, from this observation, how do we proceed to the definition of the Laplace transform? Okay, so we have at this point the formal definition of the Laplace transform. Definition of Laplace transform. Okay. The first step is define the complex variable S as sigma plus j omega. So from here it's clear that real part of S is sigma and imaginary part of S is omega. We already know the meaning of omega. Omega is the angular frequency. And sigma is now the new variable added to our definition. instead of calculating the Fourier transform of a signal directly, calculate the Fourier transform of the signal multiplied by e to minus sigma t and choose sigma, the variable sigma, the range of values of the variable sigma, such that the integral converges. Okay. The second step, step 2, is define x of s as the Laplace transform of x of t by means of the following integral. X of s is from minus infinity to plus infinity, x of t e to minus st integrated with respect to t. So, if x of t is our signal of interest, its Laplace transform is defined by means of this integral. Okay. Now, it is clear that if we substitute sigma plus j omega to this integral from minus infinity to plus infinity, x of t e to minus sigma t e to minus j omega t integrated with respect to t, and therefore this turns out to be the Fourier transform of x of t e to minus sigma t. Okay. However, there is a very important point at this step. This integral is defined by means of this expression, but how do we guarantee the existence of this integral? Okay? And choose the range of values of sigma such that this integral exists. Okay, so let us look at our original signal e to t u of t and see how we choose sigma. In fact, we have already seen that sigma must satisfy the inequality sigma greater than 1 so that the integral converges. But let us see this in the Laplace integral, the integral expression of the Laplace transform. Okay, so let us do this now. Okay, our signal x of t is e to t u of t. So x of s is therefore equal to, from minus infinity to plus infinity, x of t e to minus st integrated with respect to t. And what is s? S is the complex variable sigma plus j omega. Okay, so x of s becomes from minus infinity to plus infinity e to t u of t e to minus st integrated with respect to t. Now, because of u of t, this integral is from 0 to infinity e to t e to minus st integrated with respect to t. Okay? Now, in the evaluation of the integral, sigma plays the important role because the term j omega is just present in the complex exponential function e to minus j omega t, and we know that it is purely sinusoidal. Its real and imaginary parts are sinusoidal functions. So the only role played in the evaluation of this integral is the role of sigma. Okay? So from 0 to infinity, we have e to t, e to minus sigma t, e to minus j omega t, integrated with respect to t. So this integral exists. This integral exists if sigma is greater than 1. Because if sigma is greater than 1, the term here, the exponential term, is e to t minus sigma t, e to 1 minus sigma multiplied by t. So if sigma is greater than 1, we have a negative exponent in the exponential function, and we have decay. The exponential term decays, and therefore the integral exists. Okay, and what is the integral? Therefore, x of s is now, okay, we have this condition that should be satisfied by sigma to have a convergent integral. From 0 to infinity, we have e to 1 minus st integrated with respect to t. So the result of this integral is 1 over 1 minus s e to 1 minus st evaluated at 0 and infinity. Okay? Now, what happens when t tends to infinity? Okay, let us look at the term as t tends to infinity, e to 1 minus st. This is limit as t tends to infinity, e to t, e to minus sigma t, and e to minus j omega t. Now, as I have already mentioned, e to minus j omega t is finite in magnitude. This magnitude is in fact equal to 1. It's composed of a real part, which is a sinusoid, and the imaginary part is also sinusoid. So we have a sinusoidal function here in e to minus j omega t. And this exponential decays to 0 if sigma is greater than 1. Okay, this is equal to 0 since sigma is greater than 1. That's how we choose sigma, the range of values of sigma, such that we have a convergence. Okay, so At infinity, as t tends to infinity, the result becomes 0, and at 0, we have minus 1 over 1 minus s, or 1 over s minus 1. So, this is the Laplace transform of e to t u of t. Okay, now we know that s is a complex variable. S equal to sigma plus j omega is our complex variable. So we can just draw or sketch the complex plane, which is called the S-plane. This horizontal axis is the real axis, which is denoted by sigma, and the vertical axis is the imaginary axis, or the j omega axis. And sigma greater than 1 is just, okay, we have the point 1 here, the complex number 1 plus j0, in other words. So draw this dotted line passing through 1, which is the line sigma equal to 1. Okay, sigma greater than 1 is this region. Now, this subset of the S-plane is called the region of convergence of the Laplace transform of the signal e to t u of t. So, the subset of S, which is all those S in the form sigma plus j omega, such that sigma is greater than 1, is called the region of convergence. We abbreviate this by ROC of the Laplace transform x of s. Okay. So now it is clear that since in the Laplace transform sigma plays an important role, the region of convergence of the Laplace transform or Laplace integral is in fact determined by sigma. We always define the Laplace transform of a signal as a function expression in terms of a function of s together with the region of convergence. Without the region of convergence, the Laplace transform expression is not complete, in other words. Okay, so we can stop at this point. Thanks for watching.